Section 11.4 is all about comparison tests. There's two tests, that's why it's plural here. The first one is just your standard comparison test. So if you know that a series converges, and you are asked to find a series that happens to be less than one that you know converges, then the series you're asked about also converges. If it's the other way around, where you're given a series, AN, and you know a series that diverges, and you can tell that AN is bigger than that series that you know diverges, then AN also diverges. So a variation of that is to take a limit of the sequences on the inside of a series in ratio form. So if I have AN that is unknown and BN is known, say I know that this is convergent, and I put these two together, AN over BN, and I take that limit, if I get a constant, which is non-zero, then both AN and BN converge or diverge. So what that means is if we know BN converges, then AN also converges. If we did this and we knew ahead of time that BN diverged, then that implies that AN diverges. So they both either converge or diverge if you're able to construct this limit that goes to a constant. Okay, so let's play around with that a little bit. Here's number 3. So in number 3, we can do it both ways, and it's probably instructive to do it both ways. So let's go. First, I want to compare this to something. And so I have experience, so I can just tell you what I think when I see this. What I see is I see an n to the first power and I see an n to the third power. So I think that this is similar to 1 over n squared. That's what I think in my mind. And this converges because it's a p series. You can use the integral test to show that converges if you like. But anyway, this is the known Bn. This is the series that I know converges. So what I hope is the series that's given to me will be less than the one I know about. Okay, so that's hard right there. You have to do a little bit of analysis to make an argument that this series is less than this one. That's a little harder to do. So let me show you how you do that. What I'm going to do is I'm going to start off with the denominator here, and I'm going to say that I know for sure that 2n cubed plus 1, I know that that is bigger than n cubed. I don't start off with fractions, because fractions are a little more difficult. Once you get good at this, you can, but when you're starting out, just start off with something you know. Okay, I know for sure that that's true. And then that means, now I can flip this. I want this in the denominator ultimately, so let's put it there now. So that means 1 over 2n cubed plus 1, and 1 over n cubed. What's the relationship between those? Well, if you remember from when you did inequalities in high school or younger, when you flip this, it flips the inequality. So now I have this. That's not really what I want. I want this is less than n squared, but I can easily multiply both sides by n now. I'm multiplying by a positive number, so I don't have to worry about that sign changing. So now I get n over n cubed, which is 1 over n squared. So now I've shown that the thing I'm interested in is less than 1 over n squared. The next step, you can just put the sigma in. And there you go. Now, since this converges, you can even just write, instead of saying converges, you kind of indicate this by saying it's less than infinity. That's another way to indicate convergence. So I've now found that the one I was interested in is convergent, or it converges. Right, now let's do the same thing with the limit comparison test with the same problem. when you do the limit comparison, you still need to make a guess as to what to compare it to. N over n cubed kind of indicates the n squared in the same way that I did that here. So I'm doing the same conclusion as I did at the beginning here. I just look at it and I compare the powers and I realize this is similar to 1 over n squared. So in the same way that I guided myself towards this conclusion in the comparison test, for the limit comparison test, I'm going to use that 1 over n squared as my as the other bn in the limit comparison test. So this one is known to be convergent. Okay, so what I'm going to do is I'm going to do the limit as n goes to infinity, and I'm just going to take this whole thing over the 1 over n squared. That's the an over bn. Okay, so when I do this limit, okay, let's first clean it up a little bit. Nobody likes to have fractions within fractions, so what I'm going to do is I'm going to multiply top and bottom by n squared. And what I get is n cubed on the top, 2n cubed plus 1, and that becomes 1 on the denominator there. So this is the result. And this limit you can say is 1/2. Okay, so let's look back up at what the limit comparison test says. If you do this ratio and you get a constant in the limit, and that constant is not 0, then they either both converge or both diverge. Our n squared converges, so if they both must do the same thing, then the conclusion we come to is that this series converges. And you can say by the limit comparison test. Okay, so that takes a while to go through all that. Let's try to get one more in here. Let's do number 4. N equals 2 to infinity n cubed over n to the 4th minus 1. Alright, so again, I'm going to look at that and I'm going to say, you know, this is similar to 1 over n. Okay, because I see the n cubed, I ignore the constant here. It's really like n cubed over n to the 4th, which is 1 over n. So this is the thing I want to try to compare it to. Okay, so just like before, let's start with something that's just painfully obvious. Is it not true that n to the 4th minus 1 is less than n to the 4th? I think we can all agree with that. And so now what I really want is to flip that. So let's have 1 over n to the 4th minus 1 is greater than 1 over n to the 4th. Okay, when we flip these things, when we write the reciprocal, the sign changes, or the inequality changes. Okay, well now, but I don't want this, I want n cubed, so let's write n cubed over n to the 4th minus 1. That's still greater than n cubed over n to the 4th, and that's equal to 1 over n. So we can conclude that the sum of n cubed over n to the 4th minus 1 is greater than the sum of 1 over n, and we know that this diverges. This is the harmonic series. Okay, so n cubed over n to the 4th minus 1 diverges by comparison. Okay, let's do this one by limit comparison. So the same conclusion I draw at the beginning is what's going to help me do the limit comparison. I know this is similar to 1 over n. This was 2 actually, but it's okay. We can say this is 2 as well, if you like. Okay, so let's do that limit, right? We just do the ratio of these two, and we must conclude if we get something like a constant, then we must conclude that they both diverge because 1 over n diverges. So I'll do the limit as n goes to infinity of n cubed over n to the 4th minus 1 over 1 over n. And to clean that up, I'm going to multiply top and bottom by n. It gives me limit as n goes to infinity of n to the 4th over n to the 4th minus 1. That's equal to 1, which is not equal to 0. So I got that constant, which is not equal to 0, and so I must conclude that both series either diverge or converge. But since we know that this diverges, the harmonic series, the one that we were given, must also diverge. Diverges by limit comparison.